Hi, everyone. This is Group 19. We want to quickly talk to you about our paper, Towards Efficient Inference, Adaptively Cooperate in Heterogeneous IoT Edge Cluster. Now, let's imagine thousands of IoT devices generating continuous streams of data that require real-time analysis. Sending all of this data to the cloud introduces high latency and network congestion, which isn't acceptable for things like smart homes or autonomous systems. At the very same time, we can use something called CNN inference. This is a powerful tool for analyzing this data, but it demands computational resources that are far beyond a singular edge device. So now we face a predicament. How can we distribute CNN workloads efficiently across a network of resource-constrained, heterogeneous IoT devices? Well, there are four core obstacles we face. The first, redundant computation. Overlapping tasks across devices waste compute power. Two, communication overhead. Transmitting intermediate results between devices can outweigh performance gains. Three, heterogeneity. Devices differ widely in capability, complicating task allocation. And finally, scalability. More devices often mean more coordination and therefore more complexity. To solve this, the paper formulates an optimization problem. This means we want to achieve a stage S star that minimizes the period of the pipeline while making sure that the latency T is less than or equal to a certain value. This framework allows for balancing throughput and latency, guiding how CNN layers and devices are divided into stages. Now, the paper formulates a solution called Pico. Pico starts with a homogeneous cluster. The first stage in solving the problem is a dynamic programming solution. The algorithm considers all available devices as homogeneous. It divides the problem into finding optimal splits of both the neural network and the device allocation, and it recursively builds solutions to minimize overall throughput time. Next, we need to adapt to heterogeneous environments. We begin by identifying stages with high computational demands. We then redistribute devices to balance workload effectively, and finally adjust the feature map distribution based on device capabilities. This all ensures that workloads are matched to device capabilities, and faster devices handle more complex tasks, while slower ones aren't overwhelmed. This works in tandem with adaptive parallel scheme switching, where dynamically it's chosen between pipelined and one-stage inference based on real-time workload. This always aims to minimize latency. Now, based on this, the results are the following. When compared against other parallel strategies, Pico obtains minimum inference periods across different CPU frequencies along with maximum throughput. The average inference latency is most stable and best achieved by adaptive Pico. Although Pico does well, it faces a decline in performance in lighter workloads due to the unnecessary parallelism. And finally, it's shown that Pico remains consistent with increasing layers and devices. Now, this is all fine and dandy, but there also are some limitations. One area for future work is supporting dynamic graph partitioning. Right now, the algorithm treats each block in graph-based CNNs as a singular unit, and this limits flexibility, especially when working with complex architectures like MobileNet or DenseNet. Additionally, there is the assumption of static and equal network bandwidth. Within the real world, IoT deployments, bandwidth often fluctuates due to interference or network changes. And finally, the scale of the experiments within the paper itself were very small. Tests were conducted on just 8 devices. To prove broader applicability, the system needs to scale to larger, more diverse edge clusters. Thank you so much.